Okay. So I'm mainly here to talk about applied mathematics. Thank you, Hunter and Mr. Zimmerman, for inviting me out here. I'll admit, though, I did picture you as a slightly older German gentleman. But let's go ahead and get started here. So, speaking of mathematics, epistemology is basically how do we know what we know, right? So how do we know what we know in terms of mathematical underpinnings, pure-wise? Because I'm not going to talk about pure mathematics too much, but I'm going to talk about it just enough to get us to a framework to where we can actually speak about some of the stuff that comes out of it applied-wise. So formal logic, that's like your basic propositions, syllogisms, stuff like that. So if A equals B, B equals C, then A equals C. Basic stuff. Propositions and stuff, that's mainly what formal logic is concerned with. Informal logic is concerned with things like argumentation theory and stuff like that. So, but we won't get into that. That's basically like some of the stuff you see in literature and whatnot. So, let's talk about algebra. Analysis, topology. Okay. So, is anybody familiar with some of these terms? Okay, which ones?
Algebra and topology.
Yeah, right. So, topology concerns itself with spaces, stuff like that. Algebra mainly concerned with structures, polynomials, number theory, stuff like that. Analysis, basically, what that starts out being in undergrad. If you end up taking an undergraduate course on analysis, you'll end up going and taking this thing, which used to be called advanced calculus, but which is now called real analysis, which concerns itself with rigorously proving calculus from formal logic, propositions, set theory, sort of stuff onward. This is kind of related to that. I'm not going to talk about that, but I feel like it's necessary to sort of talk about these things being the foundational underpinning behind them. Already pure stuff. Right. Okay. So, so that's the basic gist. You have polynomials. They're sort of the poly meaning many, nomials meaning name. So it's a many named equation. So a lot of stuff you see there, and number theory, of course, which you could get more into. But let's concern ourselves with the applied stuff. So what's actually interesting is how these things lead to their applied components. So this one, that's a biggie. This one gets applied all the time. Reason being, calculus, from Leibniz and Newton all the way today, got us to the moon. Hey. So with analysis, you have this thing called, well, actually, how do I want to do this? Yeah, okay, let's go. Let's talk about PDEs. Okay, who here has heard of PDEs? Okay, so you have your regular differential equations. These are partial ones which refer to different sorts of aspects. You have like the weird looking symbol there, as opposed to the upper, a lowercase, non-curvy one, like that. So basically this will be referring to things like this thing called the heat equation. How exactly is heat distributed on a steel rod, for instance? How exactly are we going to measure how that's distributed? You can use Newton's law of cooling. I don't know if you all are familiar with that in your calc courses yet. It sort of relates to that, but it's concerned with like heat distribution, energy distribution, anything you can really look at in terms of And in terms of a distributional system relying on physical phenomena, you can use PDEs. Meteorologists, they use PDEs all the time. In fact, a lot of the stuff that they work with, apart from the data collection that lies therein, is PDEs and Python. That's the bread and butter of what they do. So you can basically, and the reason why you're able to use PDEs so well is because they can actually, as a consequence of the way that they were created, you can actually make it to where they represent more general solutions to various problems. Which sort of leads me to how exactly do we look at these problems in this day and age with the technology that we do have? I mean, PDEs, you can sit down and run your calculations all day looking at a steel rod, but how exactly are you going to actually play with that, you know? Because, let's face it, we're all mortal beings, at least maybe. And so, let's take the computational power granted to us by brilliant computer scientists, and let's combine these two into something brilliant. So, numerical analysis. Basically, what numerical analysis does is it's this good combination in between mathematics and computer science overlapping to give us mathematical models of the universe. And so one of the things you can do with numerical analysis is you can actually observe really interesting things. Like, for example, one of my professors in my graduate advanced numerical analysis class did research in biomathematics. Biomathematics, an example of what exactly goes on there. So her research was concerned with the development and the healing rate of cancer with various treatments. How exactly do you look at the rate of change of these cells and everything in response to different treatments? How exactly are they going to heal in response to chemotherapy, radiation, and the like? Well, calculate the fundamentals with PDEs, shove that into a computer, and then you got something with ease. A lot of rhymes today, but okay. So you can do stuff like that with biomathematics, and of course you can apply it to the financial sector in regards to watching stock evaluations and whatnot. But stocks. Okay, and you can apply it on, so this is mainly concerned with economic things. Also, what else do we get from here? Well, probability theory. For sure, all of us have heard of probabilities in one way or another. Well, something that starts with a simple coin toss, you monitor its distribution, and you wind up with statistics. And what you can do with that, well, that's a pretty powerful tool. All of these things fall into play. There's a bit more a simple method to it, but in terms of, like, you collect the data, you put the data in the machine, shows you what you want. If you type it in, warning, garbage in, garbage out. You know. So statistics, you can either there's pure roots to all of this stuff that relates to analysis. Statistics is its own sort of field in its own right that was sort of like co-opted by math at a time, because you had these different statisticians that came about doing their own thing, not really mathematicians, but then the mathematicians came and they rigorously proved all of it and shoved it into this madness. No. So one of the courses we offer at OU is actually this course called Applied Statistical Methods, which is all about the whole process of gathering data, shoving it into a program, and seeing exactly how we can manipulate that and see, well, manipulate order out of the chaos that we do have, and show it into, and show people digestible pieces of what we have. So that's what's going on there. PDEs, numerical analysis, probability theory, statistics. Those are sort of like the big three, unless I'm missing something. But what's interesting about this is how it's concerned mostly with things involving continuous continuity, continuous systems. So like, real numbers. There's 0, and there's 0.00000001, and then you could break that up into however many pieces you like. Algebra deals with things a bit more discretely. That's a play on words, but also something that means something. Everything means something. Discretely, so like the natural numbers, 0, no, bad. Okay, 0, 1, 2, not including 0, sorry. But countably infinite. What countably infinite means is you can map your set of numbers to these natural numbers here. Some people include 0, but a lot of people don't. It's sort of a new trend to try and include 0. 0 is an interesting number. There's a whole movie about the number 0 and how it came back with the Middle Easterns and the Indians of the medieval era. Interesting stuff there. It's actually a relatively new concept in regards to human development. 40,000 years of evolution that we barely tapped. But that's a meme. Okay, so now let's talk about the applied things you can get from algebra. This look at these rings, these groups of numbers, these structures, and that you can make out of numbers. What exactly do you get out of that applied wise? Okay, so we have this course at OU called the Applied Modern Algebra. And one of the things that it covers is this thing called coding theory. What is coding theory? Well, coding theory is another one of those intersections that lies in between mathematics and computer science. Mainly that a lot of the things that we have in computer science come out of mathematics because, well, that's the way the game goes. Coding theory, what can we get out of that? Coding theory, it encodes things. You send a message to a friend. How are you going to make sure that it's just the friend that's understanding what's in the message and somebody else, an outside observer, can't look in? Say, oh, look, that's the secret, and then we can invade and they won't know, stuff like that. So, cryptography. And cryptocurrency. No. And then just keep going until we get to Dogecoin and then it all falls. Yeah, so cryptography, stuff like that. There's also this thing called information theory, invented by Claude Shannon, brilliant mathematician in the modern era, which came to coin what our current age is now known as. Before us, there was the atomic age. Now we live in the information age. What's the whole crux of information theory? Well, it holds that there's this mathematical way of actually categorizing, quantifying information, and from that you can take it and run to actually building computers, systems of ones and zeros, which that's kind of discrete, and can you all? No, that's too far down there. So there's actually, I'm not going to write anything on the board here, but from quantum information theory, the physicists, they've been cooking stuff up with quantum mechanics, and so basically one of the things that you can do is look at the stuff that that makes up the computer's ones and zeros as not binary, but as instead existing in a state of quantum superposition, neither 1 nor 0, but occupying it in some way at the same time, all that sort of stuff. And with that, you can actually generate quantum computers which are capable of making these massive calculations due to the flexibility that lies therein. So it's like you're not just using ones and zeros, right? You're using something that's that has that superposition. So it's like, ooh, is it a 1? Is it a 0? You know, you'll never know. And it's all part of quantum mechanics and its circuitous scheme. No, but yeah, so that's some of the stuff you can get out of there. And in terms of things that are applied, topology. Now, topology, it's very wide sweeping because everybody deals with spaces. Oh yeah, this connects to string theory. Yeah, I should have. Yeah. So basically, one of the things that I'm actually doing right now as part of my grad course on PDEs is looking at these supposedly infinitely long strings, you know, which for us is just sort of a way of looking at things, but for them is an actuality. So that's how you square that circle. Topological data analysis. So one of the things that you get out of algebra proper is this thing called linear algebra, which is concerned with matrices and stuff. Why not 50 Okay. So how exactly do we get the tools of applied modern algebra to any sort of advanced degree? Matrices. Matrices are your bread and butter for dealing with a lot of this. Because how are you going to encode all of this information in something that's like one singular structure, right? I mean, you could make this long list, you know, this set, right? But are you going to like tangibly manipulate that in any sort of concrete way without matrices? So, PDEs, string theory, topology, data analysis. Let's underline that so we don't get that mixed up. Topological data analysis. So that's one of the sort of research subjects a lot of, quite a few folks I've talked to at OU, my colleagues, have been interested in. It's sort of this new thing. Basically, it's a fancy way of taking all of the pieces of information that you have from gathering statistics, insofar as I can understand it, plugging it into a matrix and putting it into something which can only be categorized as topological by virtue of the fact that you're plugging all of these information things into this sort of topological structure. You know, like is the universe shaped like? Okay, so like universe is shaped kind of like a donut, right? And can't remember the formal name. Can anybody remember the formal name of that?
Straw.
No.
We talked about how donuts and straws are the same shape in topology.
Oh, yeah. So that's actually a genus. So it's like genus 1, and this is a poorly drawn coffee mug. And so basically these things are the same thing by virtue of genus 1. Genus 1 being, of course, this hole right here, and this thing. See that? Oh, there you go, they're the same thing. I can't see anything different. You can't tell me they're different. Okay, so that's related to that. No, that's just topology. That's not topological data analysis. Okay, but what else? Oh yes, general theory of relativity is connected to this because, of course, you're dealing with these. So the way that quantum stuff and relativistic stuff are sort of related is basically you're dealing with something either ridiculously small or ridiculously fast or both. So ultimately what goes on here relates to a lot of what's going on with theories of relativity. There you go. I'm not crazy. saying that. Right. So that's what I've got so far. Have a few minutes for questions. I know it's a lot.
When it comes to topology, how did they prove or come to the conclusion that the universe was essentially a donut shape?
Yeah.
How does that work?
So that's not actually the work of topologists sort of proving things, and it's like, oh, so logically it would be a donut, you know? It's like,
Is it a frosted donut?
no.
Now you're thinking.
Yeah, it's more this dark energy sort of stuff. So this is not the work of topologists. The universe is a donut thing, not so. That's more the work of experimental data gathering from physicists shooting things up into space, or down into space, or right into space, left into space, or some combination thereof. So that's that was just more me trying to come up with the name for what it is, because I say donut, but donut's not like...
No, it's not the real term.
Yeah, it's not a mathematical term. I wish it was.
Well, what if it was?
Yeah, but what if it was? Hey, if you get enough of us going into research, we can change it.
Exactly.
Yeah.
If I write a paper on why the universe should be called a donut,
Yeah.
eventually
So,
somebody will believe me.
I think it's a torus. Torus, I think is the name of this shape, actually. So there's actually this shape called an annulus, which is basically a two-dimensional, oh, crud. Forgot to mention one. Dynamical systems, basically. That's actually how I got into the business of looking at a lot of things in terms of applied mathematics. Dynamical systems is basically looking at how do we, so some people categorize it as the statistical mechanics behind group actions. What does that mean? Take a bunch of things in a group. How exactly are we going to look at the statistics of that? What exactly is it going to do into the future? Let's look at Markov chains. Markov chains, think of them as these little data things that you can look at. And you can look at the states at which things happen and look at the flow of those events. Dynamical systems. There. Done. That's it. That's everything that needs to be known now. But yeah, this is obviously just a general overview of the applied mathematics that we offer at OU and some of the things which we kind of don't offer under the math department, but which you can sort of grab as sort of this collection of many interesting parts as a handbag from other departments, which I kind of do. Especially here, what's actually kind of funny is if you're actually interested in foundational stuff, you actually have to go across departments now, because mathematics gets splintered and stuff based on like research cost and interest and stuff like that. So yeah, that's basically I've already done this part where I go, that's the gist of it. Now do you all have any questions about it?
Cryptography.
Mm-hmm.
Has there been any situations in the past where, somebody's actually had to write that insane form of code?
Yes. Okay, so so there's this system called RSA, which basically a lot of our computers use nowadays. Every website most every website you use, most everything you log into,
Keep on going.
using some form or other of RSA cryptology. What does this stand for? Well, those are each of the people's names that are attributed to inventing it. So, RSA cryptography, it's hard to remember the specific details, but basically it's a series of, it's this thing which looks ridiculously complicated, but on the surface of it is actually quite elementary. Basically, you're using this trapdoor sort of way with prime numbers and whatnot, and the fact that those things are really hard to. So, multiply prime numbers together, keep doing that until you make this giant composite number, and then try to break that and find the original prime numbers. It's really hard to do, and so basically RSA utilizes prime factorization to sort of make that, and that was basically coded by those three gentlemen into the system which we use today, and they make a ton of money from it. There is actually something that can break it. It's speaking of quantum, there's this thing called Shor's algorithm. Shor's algorithm, it would really fail for classical computers which are dealing with binary, because you can't do all of the things that Shor's algorithm needs to do fast enough in order to prime factorize. But with quantum computation, you can just shove that into a quantum computer and bust that. So people are actually coming up with new ones. They're like, oh, you saw RSA, but what about quantum RSA? This is a DC Comics event, you know, that sort of thing. But yeah, that's good question. All right.
Do y'all wanna get like a picture?
Oh, yeah,
The
sure.
First like big map of, wonderful.
I'll go ahead and take it on this thingamajigger. That's a phone. I know. Okay, so stand right over there. It should be. Yeah, right in front of the table that's in front of the board. You should be good.
There we go. Okay.
There we go. Alright. Okay. It should just be set up automatically. Oh yeah, I'm sure. Okay. And there we go. Make gang signs if you want to. I don't care. There we go. It was a great pleasure.
Thank you. That was wonderful. Very interesting.